Hello students, today we will discuss about the types of coupling schemes. As we know that in case of a vector atomic model, the electron is moving an elliptical path and the orbital motion of the electron produces two type of motion. One is orbital angular momentum and another is due to the charge of the electron. The in a loop, when electron is moving, it will also produce and another type of momenta, that is known as orbital magnetic momentum. And until we know that both are indicated with the help of PL and mu L in our case. On the second hand, there is also another motion with attached to the orbital motion. Electron is spinning about its own axis, and due to the spin motion of the electron, again there are two type of momentas. One is mechanical momenta, that is known as spin angular momentum, and another is magnetic momentum, as the charged particle is moving in a loop, and now this magnetic momentum in our case is represented as spin magnetic momentum. And spin magnetic momentum and spin angular momentum are represented with the help of Ps and µs, which we already discussed. There are four type of vector quantities here. Due to spin, we get two angular momentas, that is mechanical motion, and this momentum has a direction, and the direction is given with the help of right hand thumb rule. We will indicate our thumb in the direction of a spin angular momenta, and the curl of the fingers give the direction of motion of electron. Similarly, in orbital angular momentum, again with the help of right hand thumb rule, we get the direction of PL. It is a vector quantity, and by curling our fingers in the direction of the motion of electron in orbit, we can give the direction of our angular momentum. These four momentas in perturbed or cause disturbance in the motion of electron, and due to that the electron will not remain in this energy state. The energy state changes by a small disturbance, and this disturbance is due to the interaction in between these four momentas or these four vector quantities, and this interaction is known as coupling. Here we are considering that there are different type of coupling schemes. There are different ways in which our four vectors can interact with each other. In first, we will discuss about the LS coupling. In case of LS coupling, we are considering that if there are two electrons here, and the first electron spin is represented by S1, and let us consider the spin of the second electron, or the spin angular momentum of the second electron is represented by S2, then the spin angular momentum of first electron is strongly interacting with the spin angular momentum of the second electron. It means this interaction in case of LS coupling is very strong. Similarly, on the second part, if this electron is moving in the orbit L1 and having orbital angular momentum of the second electron L2, the interaction between the orbital angular momentum of first electron with the second electron is large as compared to the orbital angular momentum of first electron to the spin angular momentum of the first electron. It means the spin-spin interaction and the orbit-orbit interaction, that is the orbital angular momentum strongly interact with orbital angular momentum and the spin angular momentum interact with spin angular momentum of another electron very strong, then this type of interaction is known as LS coupling. Hence, we can define that in LS coupling, the spin-spin interaction and orbit-orbit interaction is strong as compared to the spin-orbit interaction. It is here we are considering this is a very weak interaction. In maximum cases, in maximum atoms, the coupling or the interaction is found to be LS coupling. So this LS coupling also known as normal coupling. It is also known as normal coupling, and it is also known as with the third name, that is the Russell-Sanders coupling. Let us consider an example. With the help of an example, we will explain LS coupling and also we will explain the different rules of LS coupling or different characteristics of LS coupling. Let us consider there is one electron in S orbit and another electron is in p suborbit. For first electron in the S suborbit, we are considering the spin quantum number is half, and similarly for the second electron in the p orbit, we are considering again that is it is also moving in clockwise direction. For first electron, the value of orbital quantum number is equal to 0, as we know that the orbital quantum number is 0 when electron moves in the s orbit. And for the second electron, the orbital quantum number, that is L2, is equal to 1. In our LS coupling, the spin angular momentum interacts strongly with the spin angular momentum, and due to their interaction, we will get a total spin quantum number, and it is the magnitude of the addition of these two spin and taking all the possible integers or half integers to s1 minus s2. We will get in our case half plus half is equal to 1 and half minus half is equal to 0, and there is no integer lying in between them. So our total spin quantum number comes out to be 1 and 0. Similarly, in case of orbital angular momentum, our total orbital angular momentum comes out to be the addition of the two orbital quantum number to the subtraction of the two orbital quantum number. We are taking the magnitudes. It means always we have the positive values for total spin quantum number and positive values for total orbital quantum number. And in our case, L1 plus L2 is 1 as well as L1 minus L2 is 1. Hence we have single value of L and there are two values of S. On the second step, these total spin in angular momentum interacts with the orbital. Hence now there is a spin orbit weak interaction in between the total angular momentum spin and total orbital angular momentum. And for s is equal to 1 and L is equal to 1, we have total quantum number j from L plus s to L minus s including 0. L plus s in our case comes out to be 2 and L minus s comes out to be 0, and we have to take all the integers, and in between 2 and 0 we have integer 1, and we can easily represent the terms or the interaction or the new energy level energy or the new levels which comes after the splitting of the spectral lines, and we can obtain the fine spectra. With the help of this interaction we can explain the fine spectra. In our case, as L is equal to 1, it means we are indicating the p orbit, and as there are three values for L is equal to 1, it means we have three energy levels for single value of one single value of L. We have here the multiplicity, and the multiplicity in our case comes out to be 3 because there are three values of j here for single value of L, and we will put the different values of j in the subscription of p. Here multiplicity is given with the help of total spin quantum number, and it is equal to 2s plus 1. It means we have the new term value p, the having three different values of j, and there are three levels which we will have after the interaction of these two electrons. It means these two electrons will will give the three energy levels which are produced due to the disturbance or due to the interaction in between these two electrons. For s is equal to 0, we get L is equal to 1 again, and we have J is equal to 1 only because L plus S is equal to 1 and L minus S is also equal to 1 in our case. And if we represent our term value for L is equal to 1, we will represent our p orbit, and as there is a single value of j for single value of L, we have multiplicity is equal to 1, or we can also find out the multiplicity with the help of s, and we can take it as 2s plus 1, and in our case s is equal to 0, so 2s plus 1 comes out to be 1, and here j is equal to 1. It means when the total spin quantum number is equal to 0, then we have only a single interaction or single energy level, and for total quantum number 0 we can represent if one electron is moving in clockwise direction, it may be possible another electron is moving in the anti-clockwise direction, so the total spin comes out to be 0. It means the electrons are moving anti-parallel to each other. This is the condition for the singlet term value or singlet level. In case of multiple level, or for 2s plus 1 is equal to 3, or we can say that for the triplet case when s is equal to 1, both electrons are moving in clockwise direction or both the electrons are moving in the anti-clockwise direction. Hence we can represent s1 is equal to half, s2 is equal to half, and we get the total spin quantum number is equal to 1. It means both the electrons are moving in parallel direction, not in anti-parallel direction, so there should be three energy levels, which can help in finding out or explaining the fine structure of our fine spectral lines. Now we will discuss the different characteristics of our LS coupling, and the first characteristic of our LS coupling is that LSJ all are quantized. As you have also seen in our example also, there is no value lying in between 2 and 1. We are not saying that our value of j is 1.5, or here it is 0.5, or it is 1.75, or so on. Similarly, here we are not saying that the value of s is lying in having value 0.7, 0.8, or something like that. Hence, the values of LSJ, that is total orbital quantum number, total spin quantum number, and total quantum number, are quantized. They are not continuous in nature. The second characteristic of LS coupling is that L is always an integer and have value including 0. For S, we know that value of L is equal to 0. For P, we know that L is equal to 1. For D suborbit, we very well know that value of L is equal to 2. The third characteristic of LS coupling is S may be an integer if we are considering even number of electrons, and S may be an half integer if electrons are odd in number. We can explain it with an example. Let us consider we have 2 electrons and the spin of the electrons is half. It may be possible they are spinning parallel to each other, both are moving in clockwise direction. It may be possible one is moving in clockwise direction and another is moving in anti-clockwise direction. So we will have the total quantum spin quantum number in first case is 1 and the second case is 0. Here the electrons are 2, it means the electrons are even in number, so the total spin quantum numbers comes out to be an integer. In the second case, let us consider we have 3 electrons, and the different possibilities in this case is all the 3 electrons have clockwise orientation or clockwise spinning. All 2 electrons move in clockwise direction, one is in anti-clockwise direction. 2 are moving in anti-clockwise direction and one is moving in clockwise direction. And if we take the magnitude or amplitude of S, we will have in first case 3 by 2, in second case 1 by 2, and in third case again we have that is 1 by 2. As we are considering only the magnitude, we are not taking the nature whether the electron is moving in clockwise direction or anti-clockwise direction when we are taking the total spin angular momentum. Hence in this case, when there are 3 electrons, we have half integral multiple of the value of S, and S may be an half integral value if the total electrons are odd, and it may be an integral value when the number of electrons are even in number. The fourth characteristic is that J, that is our total quantum number, it is an integer if s is an integer, or it is an half integer again if s is an half integer. The value of j is always positive and quantized, and it's in whether it is an integral or it is an half integral, the value depends only upon the number of electrons, that is the value of s in our case. The number of values of j, that is the multiplicity number, we can say depends on whether L is greater than S or L is smaller than S. When the orbital total quantum number is greater than S, then the multiplicity comes out to be a number of 2s plus 1. And when the spin total quantum number is greater than the orbital quantum number, the multiplicity number or the number of values of j for the value of L comes out to be 2L plus 1. Hence, this is our LS coupling. And the second type of coupling is our JJ coupling. And in case of JJ coupling, we are considering that the spin orbit interaction is strong as compared to the spin-spin interaction or orbit-orbit interaction. In the first case, we considered, in LS coupling, we considered that the spin quantum number, that is, or we can say that spin angular momentum of a first electron and spin angular momentum of second electron, they combined or coupled together or interact strongly to give us the total spin angular momentum. And the orbital angular momentum of first electron coupled with the orbital angular momentum of the second electron and give us the total orbital angular momentum. We considered that in case of LS coupling, the first electron spins around the total spin angular momentum, and similarly the second electron also spins around the total spin angular momentum. Similarly, the orbital angular momentum of first electrons is in the direction or spins around the total angular momentum, that is orbital angular momentum, and similarly in the second case the second electron is also precessing around the resultant or the total orbital angular momentum. But in case of JJ coupling, here we are considering that spin angular momentum of first electron couples strongly with the orbital angular momentum of the first electron and gives us the total angular momentum of the first electron. Similarly, the spin angular momentum of the second electron couples with the spin angular momentum of the second electron to give the total angular momentum of the second electron. Here the spin angular momentum presses around the total angular momentum, orbital angular momentum also presses around the total angular momentum. Similarly, this happens in the case of second electron also. Now these two total angular momentum of first electron and second electron now couples together to give us the total angular momentum of our system of two electrons. Here J1, J2 interact, and with the help of parallelogram law of vector addition, we will have our total angular momentum or total momentum in case of JJ coupling. Whereas in LS coupling, we get total spin angular momentum, total orbital angular momentum, and after taking these total spin and total orbital angular momentum, they interact weakly to give the total angular momentum. With the help of parallelogram law of vector addition, we can easily find out the value of J in our case. This is the difference in between JJ coupling and LS coupling. If we take the example of JJ coupling, let us consider again we have two electrons, one is in s suborbit and other is in p suborbit, and having spin half and spin half of second electron, also having orbital quantum number 0 and orbital quantum number 1. In for the first electron in JJ coupling, we will have total angular momentum, and it is given by with the help of spin and orbital interaction, and we will have the values from L1 plus S1 to L1 minus S1, and we are taking the magnitude only. It means all the values of J1 comes out to be positive values, and in our case J1 here is only half, whether we will take L1 plus S1 or L1 minus S1. If we will find out similarly the total quantum number angular momentum for the second electron, we will have half plus 1 to half minus 1, and we will have 3 by 2 and 1 by 2 as result. And to get the total value or total angular momentum J, for J1 is equal to half and J2 is equal to 3 by 2. As we have two values of J2, that is 3 by 2 and 1 by 2, we will consider J2 as 3 by 2 first, and in the second case we will consider J2 as 1 by 2, and in our case the total angular momentum comes out to be, that is J1 plus J2 to J1 minus J2 considering all the integers, and we will get, if we will add both these we will get 2, and if we subtract these we will get 1. Hence in this case we have total angular momentum with total quantum number 2 and 1. For the second case we are taking J2 is equal to half and J1 is equal to half. Then for J1 is equal to half and J2 is equal to half, we have total quantum number, that is addition of these is 1 and subtraction of these is 0. We will get the total angular momentum with the help of our total quantum number, as we very well know that the total quantum number angular momentum is given by J star H cross, and J star is nothing, it is under root of J into J plus 1 H cross, and we will have the fixed orientation in fixed direction as well as with fixed magnitude. It means the possible interactions can change the orientation with a particular direction, and the magnitude of the orientation with a particular change in the magnitude. All possible direction, it is not possible that these interaction can create all type of possible orientation. These interaction change the orbits with in direction as well as in magnitude in particular manner, and hence they are quantized in nature. It means these disturbances produced due to the interaction between spin orbit, quantum numbers or spin orbit angular momentum, they are quantized in nature, in direction as well as in magnitude.